Of all the strange and counterintuitive phenomena that quantum mechanics has revealed about the nature of reality, there is one that has captured the imagination of scientists, philosophers, and curious people more than almost any other. It is called quantum entanglement, and it has been described in ways ranging from the poetic to the absurd. It has been invoked to justify claims about telepathy, instant communication across the universe, consciousness, and all manner of things that have nothing to do with it. Albert Einstein himself famously dismissed it as spooky action at a distance, a phrase he intended as a criticism, a sign that something must be wrong with quantum mechanics. He was convinced that no reasonable theory of physics could permit what entanglement seemed to imply. And yet, decades of increasingly precise experiments have confirmed beyond any serious scientific doubt that entanglement is real, that Einstein was wrong to reject it, and that it is one of the most profound and useful phenomena ever discovered. So today, we are going to explain what quantum entanglement actually is, strip away the mythology around it, and explore why it matters, particularly for the future of quantum computing and quantum communication. To understand entanglement, you need to first understand a core idea in quantum mechanics: the concept of quantum state. Every particle in the universe, an electron, a photon, an atom, has a set of physical properties. Things like spin, polarization, energy. In classical physics, these properties always have definite values. An electron is either spinning up or spinning down, full stop. But in quantum mechanics, before you measure a particle, it does not necessarily have a definite value for these properties. It exists in a superposition, a mathematical combination of multiple possible states at once. The act of measurement forces the particle to resolve into one definite outcome. But before that measurement, the superposition is genuinely real. It is not that the particle secretly had a value all along, and we just did not know it. Experiments have ruled that interpretation out. The indefiniteness before measurement is a fundamental feature of reality at the quantum scale. Now here is where entanglement enters. When two particles interact in certain ways, or are created together under the right conditions, their quantum states can become linked in a way that cannot be described independently. The two particles form a single, shared quantum state. They become entangled. And what this means, in practice, is this. When you measure one of the entangled particles and it resolves into a definite state, the other particle, no matter how far away it is, instantly resolves into a correlated state. If you measure the spin of one entangled electron and find it is spinning up, you will always find its entangled partner spinning down. And this correlation holds regardless of the distance between them. They could be in the same room, or they could be on opposite sides of the galaxy. The correlation is instantaneous. This is exactly what troubled Einstein. It seemed to violate his theory of special relativity, which holds that nothing, no information, no influence, no signal, can travel faster than the speed of light. If measuring one particle instantly affects its partner across any distance, is that not a faster-than-light influence? This tension is real, and it took decades of careful thinking to resolve. The resolution is subtle and important. While the correlation between entangled particles is instantaneous, it cannot be used to transmit information faster than light. Here is why. When you measure your entangled particle, you get a random outcome, spin up or spin down, with equal probability. Your partner, measuring their particle, also gets a random outcome. The correlations only become visible when you compare your results afterward, through a classical communication channel that is limited by the speed of light. There is no way to use entanglement to send a message, because you cannot control what result your particle gives you when you measure it. The universe has arranged things in a way that preserves the speed limit, even while allowing these deeply non-local correlations to exist. The proof that entanglement is real, and that Einstein's preferred alternative, the idea that particles carry hidden predetermined values, is wrong, comes from a series of experiments testing what are called Bell inequalities. In the 1960s, physicist John Bell showed mathematically that if particles carried hidden preset values, the correlations between measurements on separated particles would have to obey certain statistical limits. Quantum mechanics predicts those limits would be violated. Experiments, beginning in the 1970s and becoming increasingly rigorous over the following decades, have consistently found that nature violates Bell's inequalities, exactly as quantum mechanics predicts. The most airtight of these tests, called loophole-free Bell tests, were first performed in 2015 by a team in the Netherlands. The conclusion is inescapable. Entanglement is a real feature of nature, and the correlations it produces cannot be explained by any local hidden variable theory. John Clauser, Alain Aspect, and Anton Zeilinger were awarded the Nobel Prize in Physics in 2022, specifically for their experimental work establishing this. So why does all of this matter for quantum computing? Entanglement is not just a philosophical curiosity. It is one of the core resources that quantum computers exploit to do things that classical computers cannot. When qubits in a quantum computer become entangled with one another, they form a shared quantum state whose complexity grows exponentially with the number of qubits. A system of 300 entangled qubits can exist in a superposition of more states simultaneously than there are atoms in the observable universe. The quantum algorithms that offer computational advantages, Shor's algorithm for factoring, Grover's algorithm for searching, algorithms for simulating quantum chemistry, all rely on entanglement as a fundamental ingredient. Without entanglement, a quantum computer would offer no advantage over a classical one. It is that important. Entanglement also plays a central role in quantum communication. A protocol called quantum key distribution uses entangled particles to establish cryptographic keys between two parties in a way that is theoretically secure against any eavesdropper, including one with a quantum computer. Any attempt to intercept or measure the entangled particles disturbs their quantum state in a detectable way, alerting the communicating parties that their channel has been compromised. This is not faster than light communication. It requires a classical channel too. But it offers a form of security that is grounded in the laws of physics, rather than in computational hardness. Quantum entanglement is one of those rare scientific discoveries that genuinely changes your understanding of what reality is. It tells us that the universe is, at its deepest level, non-local, that separated particles can share a single quantum state, and that the act of measurement on one part of that state has immediate consequences for the other, no matter the distance. Einstein spent the last decades of his life convinced this could not be right. The universe, it turns out, did not share his discomfort. Entanglement is real. It is experimentally confirmed. It is Nobel Prize-winning physics, and it is one of the most powerful tools we have found for building the technologies of the quantum age.